Good morning, everyone. I am a PhD student from the University of Florence, and this work, frequency being entanglement-based quantum key distribution, has been done in collaboration with University of Pavia. So nowadays, we have that the digital data traffic is increasing more and more, and this demands for higher performing quantum systems. So in particular, we're interested in two figures of merit, the secure key rate and the maximum achievable distance link. The main limitations come from noise and losses in the quantum channel. So it is possible to adopt different type of encoding protocols, but personally I think that the most interesting one are those that pave the way towards higher dimensional systems, since those type of qubits are more robust to noise. So a typical encoding scheme is time being and phase encoding, where we have two time beams here, and we look at the arrival time of the photons in the Z basis, and we have a coherent superposition of the two in the X basis, and we look at the relative phase. These type of systems are particularly used for fiber-based communications, since they are robust to bit flip and phase flip errors. However, they require high precision clock stabilization and the stabilization of imbalanced interferometers. If you combine time being and path encoding, you can move to higher dimensions. So for example, here we move to 4 dimension by using a multi-core fiber. And it was possible to exchange a secure key over a 52-kilometer fiber length. But this is a very big interferometer, so we also needed to implement active phase stabilization. In parallel to the protocol development, we also have hardware improvements. And very interesting is that of photonic integrated platforms. So here I show you an example of the miniaturization of our receiver unit. So you can see a fiber-based interferometer that's 45 by 45 centimeters square, and we reduced it down to 5 by 5 centimeters square, integrating it into a glass chip. So not only the system dramatically reduced in size, but it was also more stable. So if we look over here at the secure key rate against the attenuation channel, we can achieve a longer link in using this integrated interferometer. And for all of the other data points, we have more key, that is, we are able to extract more key for the integrated interferometer other than the fiber base. So improving the stability also means improving the performance of the system. So in a photonic integrated platform, there are natural choices of encoding, which can be path encoding, but more interesting, frequency being encoding. And this is actually the chip that we use for our experiment. This is a silicon chip where we have a bus waveguide that's coupled to 2 rings. And here you can see the transmission of the 2 frequency comb that we generated, pumping these 2 rings. And on top, we have metallic heater to optimize the transmission of the rings. So this system is inherently high dimensional because there are actually more rings coupled to the same bus waveguide, and by just pumping more, we're able to increase the comb lines in the frequency comb. But for the sake of our experiment, we now focus to 2-dimensional systems. So first, we characterize the ring resonator sources. We have the brightness of the photon pair sources that up to 0.1 milliwatt follow a quadratic behavior. After that, we have a deviation due to 2 photon absorption and induced free carrier absorption in this silicon chip. Then we have the bell fringe here, where we measure the visibility of the 2 photon interference. Without correcting for accidental counts, we have a visibility of 89.5%, while correcting for accidental counts, we can increase it to 93%. And this is actually because the 2 rings are slightly different in order to be able to distinguish between the combs. Then we perform quantum state tomography. You can see here the reconstructed density matrix with a fidelity of 94.1%. And we also look at the correlation matrix, where we see that there are high correlation between plus plus and minus minus states in the XX subspace, and 0, 0, and 1, 1 for the ZZ subspace. Okay, so now that our system is ready and characterized, we can move to the experiment. We start over here with a pump laser and a control laser that are brought together in a beam splitter. And then we have a phase modulator that from the baseband frequency creates two sidebands of equal intensity. Then we separate the control laser from the pump. The pump is then amplified with this erbium-doped amplifier. So before that, we need a fiber polarization controller and a fiber polarizer to match the polarization of the amplifier. An isolator protects the amplifier from back-reflected light. And then we filter the signal to have 3 clear comb lines without any residual noise. Then we remove one of the 3 comb lines with this combination of a circulator and a fiber Bragg grating, because we're only pumping 2 rings. And then we go into the chip and we actually pump the rings and we generate the signal and idler combs. We separate the idler from the signal and the pump. And with this beam splitter, we recover an error signal. So we look at the transmission through the chip, and the error signal is used with an FPGA to actively control the heaters into the chip, such that each comb line is locked to a specific ring. Then we clear the pump, and we mix the signal with the control laser, and they travel together into the fiber spool. I will get to the control laser in just a little bit. At the output, we have the 2 detection stages, Alice and Bob, and they are equal. Now, you can see here that we only had 6 detectors to measure the 16 projective measurements instead of the natural 8 that you would need. And we managed to make it work by adding these fiber delay lines, such that the coincidence peak was shifting in time, and we were able to recover all of the combinations. So for the X basis measurement, we mix the frequency beams over here with a phase modulator. While for the Z measurement, we simply separate the 2 time beams. Now, what we noticed at the beginning was that even for just an 8-kilometer fiber, the Q-bar started to drift after a few seconds of measurements. And the same happened to the fidelity of the density matrix. And by looking in more details, we noticed that a dephasing was happening in the XX correlation subspace, meaning that we were no longer measuring correlation between plus plus and minus minus, so the state was actually shifting over time. And we linked this shift to the temperature fluctuations in the lab. So actually the optical path length into the fiber spool was changing, so we had this dephasing. And this is where this control laser came in, and so we send it together into the fiber spool with the signal photons, and it's composed of 3 combs. At the output, we additionally modulate the control laser, and by filtering for the baseband frequency and changing the RF power, we were able to measure the drift, so to actively compensate for it by acting on the other phase modulators. And with this in mind, we noticed that in the locked case scenario, as we called it, the Q-bar was stable. Now I show you here the data for 10 minutes, but the system actually was running for hours. And we were able to stabilize both the Q-bar and so also the fidelity of the state. So we performed a secure key rate analysis, where we have first an infinite key analysis, where we account for the bits disclosed during the error correction by taking the binary entropy of the Q-bar in the Z basis. Then we accounted for bits disclosed during privacy amplification, for the sifting, so the basis reconciliation, the generation rate, the channel attenuation, and the detector's efficiency. Then, after that, we also accounted for finite size effects. So we subtracted a term accounting for the block size and one accounting for the block time. So the first term means that the probability of the final key being less than the difference between the secure key rate in the infinite key analysis and this delta term is at most epsilon security, while the lambda term means that the probability of Alice and Bob key differing at the end of the protocol is at most epsilon correction, and both these epsilon terms are set to the order of 10 to the minus 12. So we have our final results. This dashed line is the simulation curve that we did in the infinite case analysis. And then we analyzed the data for different block sizes. So for block sizes up to 10 to the 6, we are able to extract a key for 26 kilometer fiber spool. But as we decrease it to 10 to the 5 and even down to 10 to the 4, we were only able to extract the key for 2.6 kilometer fiber spool. So in conclusion, we demonstrate QKD using frequency bin encoding, and a key finding has been that this type of encoding needs an active phase compensation for the propagation into the fiber spool. And the fact that we have an integrated platform to generate the entangled state ensures stability of the system, and also it enables us to scale it up to higher dimension. So with our work, we paved the way for higher dimensional encoding with frequency bin. Now, I would like to acknowledge my team and everybody that worked in this experiment, and thank you for your attention.
Thanks for your great talk. Question time.
Thank you for the great talk. I had a question about the frequency drifts, I guess, that you were explaining and why you needed the active feedback. So how quickly does, I guess, the drifts occur so that you basically now need this active phase stabilization?
So for shorter fiber spool, you can take data for 10 or 15 minutes, and that's not a big problem. But as you can see here, for 8 kilometers, which is not that long a distance, after a few seconds here, you see that the system starts to drift. And this is the 26 kilometer case, where, I mean, you see that after a minute and a half, then you need to activate the stabilization system.
Any other questions?
Can you say more how you do the detection for the X spaces, for the two frequency bins?
Yeah, so for the X-space this detection, so the state that we generate is 0, 0 plus 1, 1. So we activate the phase modulator to introduce a phase between the 0 and the 1 state. And then you have a first circulator, then a filter, so the light that passes through goes through the second circulator, is reflected back by the second filter, and is detected by detector 2. By the other one, just gets reflected by this grating and gets sent to detector 1.
Okay,
Thank you.
Yeah, over here. I also had a question about the phase stabilization procedure. I guess one is a bit more technical, which is, do you have an idea of roughly what the error that is remaining at the end of your stabilization procedure? So I guess if you don't phase stabilize, you'll have some phase error. But if you do phase stabilize, I guess there's still some remaining error. Do you have an idea of roughly what that is?
I mean, so there is still some error, and it's quantified by this Q-bar in the X spaces, where, I mean, only the X spaces goes through the dephasing because you're adding a phase between the two time beams. So you need to compensate only in that basis. And there still remains some kind of error, but if you compare this with the unlocked case, for example, with no fiber spool, they are very comparable with or without the phase stabilization active.
Okay. Okay, thank you.
Thank you.
We can have one more question. Okay, thank you for a speech. I would like to want to know how the active phase compensation is achieved.
Okay, so So this is a more detailed example of how we achieve this phase stabilization. So we have the control laser that gets first a first phase modulation. So from the baseband frequency, you create the two combs. So you have three combs that travel into the fiber spool, and at the output down here, you modulate again these three frequencies. So you have this state at the output, and theta is the dephasing that occurs into the fiber spool, while phi is what you control with the phase modulator. So when you filter for the baseband frequency, so just the term nu zero, you have that you can measure the intensity. So you can measure the dephasing between theta and phi with this term. So basically, this is an interferometer in frequency. So once you can measure, you know what's your dephasing, and you can correct for it by acting on the other phases modulators.
Okay, thank you.
Yeah.
Okay, let's thank Giulia again for the great talk.
Thank you.